Hello and welcome back this week. Um, is anybody new this week that wasn't here last week or streaming? Okay. I won't go through my whole long introduction, but I'm Augustine Icapelli. I'm the instructor for this class. I have a background in meteorology, although I have not actually been a meteorologist for a long time. I did that early in my career, and that's what brought me down to the Wichita, Kansas area. Nowadays, I am a director over at the WSU West location over across town, and then I teach meteorology on the side, in addition to running a local microbrewery along with my wife. So that's kind of what keeps me occupied most of the time. Some quick housekeeping. The bathrooms, just kind of like before last week when we were at the other location, they are just outside these doors. You can feel free to get up, stand up, stretch if you need to, go to the bathroom at any time. You're not going to upset me or anything like that. So feel free to use the restroom at your convenience. We will break, kind of depending on how fast or slow I go through the lecturing material. We'll break about 50 minutes into the class for about 10 minutes, and then we'll reconvene for another about 50 minutes or so, and take some questions right at the end, and then send you on your way. So another thing they wanted me to add on today is a reminder. Ironically, I'm not wearing one right now because I was told that I could not. I didn't have to up here, but reminder about face coverings. Students, faculty, staff, and visitors must wear face coverings over their mouths and noses while on all Wichita State University campuses, in all hallways, public spaces, classrooms, and other common areas of campus buildings. I see everybody's got that, so we're good. Also, feel free to break in at any time and ask questions. I think in this space, because we've got the higher ceiling, you're going to kind of have to speak up a little bit for me, and then I will try, or come up here to the microphones if you don't have a loud projecting voice. And then I will do the best I can to rephrase your question for our remote audience. And then for those of you who are remote, remember you have the option to email in questions, and they'll be brought to me periodically, and I'll answer those as we go through the class. So feel free to speak up. I think we did have a question. Was it related to the past material, current material, or just kind of stuff on the side? Okay, perfect. Just wanted to make sure I didn't miss you. So yeah, either grab me at the break or grab me at the end. So just kind of a quick review. Last week, we talked about the basics and history of meteorology, including kind of really what we got around to is how relatively young as of a science meteorology is. Most of our modern day equipment that we use in meteorology to take all of our readings that we analyze and work with, those were all developed pretty much within the last few hundred years, at least in terms of the modern equipment. And so in terms of our ability to observe our entire globe at one particular time, at any given moment in time, that's a very, very new thing for us. Really, in the space age is the first time we're able to look at the entire planet all at one time and get a good, consistent set of readings all over the planet for kind of analysis of weather conditions, and that is what helps aid our modern forecasting. This week, we're going to get into, well, on the front end, these two are kind of reversed because we're going to tackle them in the opposite order. Severe weather and forecasting. So the first half of our class here, we're going to go through a little bit of the, especially on the front end of the day in the life of a meteorologist, operational meteorologist. And then on the second half of the day, we'll talk a little bit about severe weather and supercells, things like that. Next week, we're going to get into winter weather winter weather forecasting, and also talk about the storm that sank the Edmund Fitzgerald, which kind of gets into mid-latitude cyclones. So we'll talk about those two things because they kind of go hand in hand. And then finally, on our fourth day of class, we will go into we've gone from the past, and now we're going to be looking into the future, talking about climatology and climate forecasting. So as I mentioned in the first class a little bit, and then here just a few minutes ago, I did graduate with a degree in meteorology. Didn't use it for very long, at least day to day. I worked for a commercial weather firm downtown. At the time, it was called Weather Data Incorporated. It was owned and operated by Mike Smith, who those of you who have lived here in the Wichita area for a long time, Mike was a fairly long time head meteorologist at Channel 3. And he kind of used that as a platform to start his weather firm. In the last about 10 years or so, Weather Data was bought out by AccuWeather. And so now it's a division of AccuWeather, which is big name in commercial meteorology as well as consumer meteorology. So during my average shift, which when I first started as a meteorologist, started at about 11 to 11:30 at night and went until usually about 9-ish in the morning. So sometimes some pretty long days there, and during the night. Also part of the reason why I don't do it anymore. Meteorology is not necessarily it's not always a lucrative career, and it's also a career that you're kind of always on call 24/7 to a certain extent. And there's always stuff going on. And Weather Data and now AccuWeather, they're open, 24 hours a day. Their operations floor is always manned with people watching the weather for their clients. So when I would come in, my first thing that I would do is literally print up, get all of my weather charts, both at the surface level and then all the way up to the upper parts of the troposphere, which is the lowest level of the atmosphere. And what I was looking for is to find all of my highs, my lows, my boundaries, fronts, all of these little pieces that contribute to what was going on in the weather. I would then start looking at some of the models and what the numerical models were projecting relative to what we were seeing happen and looking forward. So you would kind of use the models that would come out as some guidance, but you always had to use this in conjunction with the models, because remember, garbage in, garbage out sometimes on numerical models, and different models handle different weather situations, sometimes better, sometimes not so good. So there was always the need for the human. We can't just let a computer just spit out our forecasting for us. We also have to kind of apply our own understanding of meteorology to the situation. So really about the first almost half of my shift would just be analyzing all my charts. And that's literally just kind of, at the time it was just drawing every, the lines on every chart and identifying all of the features that were potential contributors to the weather that would be occurring in my forecast periods. Then once I kind of had the situation at hand, it's a matter of looking at, okay, where are the different cities that I'm forecasting for? When I was a forecaster, I had clients from Providence, Rhode Island, all the way to San Diego. Newspaper clients as well as utility clients. Had some municipalities, some cities that needed specialized forecasting. So once you had your picture put together, then it became much easier to say, okay, well, this, for Rhode Island, for example, it's going to be this and this and this based upon what I've generated and what I see going forward. And then you just kind of plug all of those things in. In my case, we at the time had some newspaper clients, so I would put together all my maps and hand it off to the assistant who would wind up doing all the drawing of the maps for the newspapers and things like that, and start plugging in all of my forecast numbers for the cities across the U.S. And then finally, you'd spend time basically just publishing all of your forecasts, which is just getting them out to all of the different clients. And that was something that we do in conjunction with the other couple of people in our department at that time. So this afternoon, we're going to mostly just focus on that first step, which is analyzing what's going on in the atmosphere, because that is really the heart of what we do as meteorologists, and that feeds everything else. And plus, it also takes a fair amount of time as well on its own, as you can see here. So when we are analyzing the current conditions, we're printing out the surface map, which that's, same kind of map that you're oftentimes seeing on the news, on the weather forecast. They're usually just showing you that surface level map with your highs, your lows, your fronts, and that sort of thing. But it's important for us as meteorologists to understand not just what's going on at the surface, but what's going on above the surface, because all of that feeds into what the potential is, in particular for precipitation, and even in more extreme cases, severe weather. That story can't be told just looking at the surface level. You've got to look at the aloft levels as well. So once we had all of those printed out, we would start drawing what are called ISO lines. And they're basically they're lines of equal something. Most often, we would draw our lines of equal temperature, our lines of equal dew point, our lines of equal barometric pressure. Now, remember, we talked about millibars and inches of mercury. And on weather charts, we use millibars. So we'll look at that here in just a little bit. And then once we've got all of those lines drawn, looking at what the moisture is in the air, looking at what the temperature is across our chart, and looking at where the highest and lowest pressures are, once I've got all of that information, it becomes considerably easier for me to find and identify where the frontal boundaries are, where our highs and lows are, and start really kind of wrapping my head around what the weather is going to be like in the next 24, 48 hours. So we're going to come back to this image quick. I actually wanted to move this around in my slide order, and then realized that was probably going to cause more trouble to these guys than it was worth. But this we're going to go through, and I'm going to, in smaller classes, we do this kind of as a group project and kind of break out and kind of work together on analyzing the map. I'm going to kind of do it for you, and if you can kind of watch and feel free to pipe in with any questions, any things that you see me doing that seem a little odd or don't make sense to you. But first, we're going to look at what each one of these little things means. And that is the standard station model that we're looking at, in this case, Great Bend there. So when a meteorologist is analyzing a map, especially with the surface map in particular, here, we're going to be analyzing lines of equal temperature. Oftentimes, those are, as a meteorologist doing it, kind of like what you see on a weather map that's for public consumption, we're analyzing about every 10 degrees. Sometimes if a meteorologist is trying to tease out a frontal boundary, they might analyze a couple isotherms at 5 degrees, but typically it's about a 10-degree interval. And then we're going to analyze there's a mouthful, isodrosotherm. Those are lines of equal dew point. And dew point's very important because it tells us how much humidity, how much moisture is being pushed into a particular area. And especially as we get into discussing severe weather, humidity is really important. You've got to have your boundary, you've got to have your humidity, you've got to have some shifting winds aloft. If you've got all of those things, then you start having potential for severe weather. And so that's why we need the temperature and we need the dew points. We're going to then look at where the location of the highest pressures are and the lowest pressures. We're going to look to see if there's any precipitation we need to address on the map and notate. And then we're going to finally, once we've got all of that, it becomes a lot easier for us to find those front and trough lines on our map. So this is kind of like, although it's colored differently on here, but this is sort of what we see as meteorologists when we're looking at a weather chart. It's always the same way, and it's sometimes you won't see each individual mark on the map. In fact, most often you won't see unless there's some extreme changes in pressure. This oftentimes doesn't get put onto the individual plots. And then right here, if there's not precipitation going on, you don't see any precipitation here. But you will always see, as long as the temperature and weather sensors at that particular station are working properly, you'll always get a temperature, you'll get a dew point, you'll get that wind direction and sky cover, and then you'll get this sea level pressure. Now, that sea level pressure that you're seeing here, remember we talked about how the average sea level pressure in millibars was 1013.25. Well, most of the time, unless we have very low pressure, our pressures are always going to be 10 something. And so what we do on these charts is the front 10 is just kind of dropped off. So this really is saying here 1010.7 millibars is how you read that. Now, if you were to see a 9 something, that would mean that the pressure is actually under 1,000 millibars. So you're in a real low pressure area. You only get into some of those extremes when you're talking about in hurricanes primarily, and then also in deep mid-latitude cyclones like the storm that sunk the Edmund Fitzgerald, which we'll talk about next week. So now I'm going to go ahead. Any questions about any of this before I back up? Yes?
On your symbols up there, on the wind symbol,
yeah.
it looks like there's kind of an F on there.
I'm sorry. I should have covered that a little bit more. Yeah, the wind here is, that's showing the direction that the wind's coming from. So that's the long bar into the center there. And then the long hash here is 10 knots. And then the short one is 5 knots. Now, there is another symbol that you would rarely see on a surface map, but is very common on the upper air charts where the winds are much higher, is you'll see kind of a blackened triangle, which is 50 knots. So that's what that, good question. Yeah, I just kind of blazed right over that. And then, yeah, this center portion, which is the sky cover, in this case, it's clear. If it's totally blacked out, it's overcast. And then there's various other symbols related to how much of the sky is covered. Anything else? Okay. I'm going to go ahead and we're going to kind of walk through how I would analyze this chart. And like I said, I think most of you probably have your slide printed really small. So following along drawing on your slide is probably going to be a little tough. But just kind of stay with me, and we're going to draw on this. You're going to also see how the bias of the individual forecaster kind of comes into play here. And this is why it's always important for the meteorologists themselves to just also draw their lines and analyze their map, and not just take a computer analysis, which when we're comparing what we do here in a little bit, once I get through all of this, we're going to see how a computer drew the same thing that I'm drawing right here. This is a map from just kind of some random time when I grabbed it probably a couple of weeks ago. It's not a real exciting map, but we'll see how things kind of start teasing out. And the map is going to start looking like something that, aside of my bad penmanship on a computer, it's going to start looking like a weather map. So the first thing that most meteorologists will do, actually, truly the first thing, is typically the isobars, but I'm going to get to that one last. I'm going to start in the order that we had it on the previous slide, with our temperatures. So what I'm going to do is try to figure out, okay, what is the temperature line that I want to draw first? We see some 50s, some 60s here. I'm looking across a chart. I don't actually see on this chart, I don't think I did earlier either, any 70s. So really, I'm primarily on this regional chart looking at dividing the 60s from the 50s on this chart, for the most part. And so oftentimes you're just kind of trying to find a space on the map to kind of just get started. So I'm going to just start drawing a line right here. And I am literally trying to split the 60s from the 50s on the chart. And a lot of the time, I already did that wrong. You'll see, and this is another thing that meteorologists go through a lot of when they're doing their charts, is erasers. So we're going to back that back out. And I'm going to try to come down again like this. Yeah, actually, that's right. I wanted to go that way with it. And so I'm keeping all in this case, all the 50s, or fairly close to all the 50s. Sometimes meteorologists will just kind of smooth things out, and as a result, kind of drop out some stations here and there that maybe don't quite fit what we're looking for. And this, I don't have nearly enough space to do this up here. And so I'm coming around like that, keeping the 60s to, well, what would be my right here. And we're going to go kind of right through that one and up around just like that. And yep, we'll just kind of finish that up. I actually have no idea if that's above or below 60, so we're just going to kind of come up like that. So that's a line of 60s. I do have some 50s right down here, so I am going to go ahead and draw that in. Those slightly lower temperatures aren't necessarily associated with any, frontal boundary or anything like that. We're always also trying to keep in mind what the topography is. So right, through Colorado, we have higher mountain regions, things like that. And so the topography out west plays a big role in our isobar, or isotherms rather, as we're drawing these out. Let me see what else I might feel like drawing in. I think on the isotherms, that's about what I was doing. And you might have some 70s. You probably have some 70s just off the chart down here, but everything else looks pretty good. The isotherms are really straightforward on this map. And I'm already seeing, even by drawing these isotherms, as a meteorologist, I'm already thinking, okay, there's something that's going on here across, central western Kansas, that's driving some of the temperatures down. I'm already thinking there's some sort of high pressure system. Something's pushing down across across Kansas, across the Plains states. And so as I'm drawing, I'm also kind of thinking through what I'm seeing as I'm drawing things out. So the next thing that I'm going to draw is the isodrosotherms. Now these ones are oftentimes a little bit less straightforward than the isotherms, because what we're again trying to come up with as we're looking at this map is, okay, where is the moisture coming up into the area? This is where we're trying to start thinking, okay, where are areas that might have the potential for some precipitation in the near term forecast periods. So as I'm looking across here, we do have like an under 50 right here. I'm probably not going to analyze that one. And the reason being, it's just one point that is under 50. But we've got 50s and we've got 60s on here. I don't think we have 70s, so we won't analyze that. So I'm going to come up right here because I see a 60 right here and a 60 right here. And I'm going to start a line going like this. We do have some slightly lower under 60s here. So we've just kind of got a little bit of maybe higher humidity here in the high plains. Some meteorologists might just leave that off if they were just analyzing this regional chart. But there is a little bit of moisture there. I'm going to move kind of across and start looking kind of in the eastern Kansas, Missouri sort of area. And a lot of times, especially during the summer, we're going to look in that area because that's where our moisture is coming up into the Central Plains. We've got this big old thing called the Gulf of Mexico, and that is a very key player in especially our summertime weather here in the Central Plains. And so I do have another 60-degree isodrosotherm that I'm going to start drawing. And I'm going to come up like this, cutting, but again, between the 60s and the 50s as best I can. And I'm going to come up like that. And again, we're just kind of cutting between the two as best we can. There are a couple of stations that are under 60 that I'm cutting into this area, which we could separately analyze. And I'll show you that in just a second. So I'm coming up like that. Yeah, we do have this one station that's a 60. If I wanted to, I could kind of go something like that. And then there are a couple of stations right here that are just a little bit under 60, and we could analyze those separately as well. But what we're really seeing here is that there is a fair amount of moisture in the area. But what I do know just by looking at this, this is where I'm kind of also, again, you're thinking as you're drawing, I'm seeing all of this going, all the winds are kind of going in a southern or north, coming from the north and going south. So even though there's a lot of moisture in this area, the moisture is not sticking around. It's actually getting pushed out of the area. So now I'm already thinking as a meteorologist, okay, if cold air is pushing south and pushing the moisture out, there's probably somewhere on here going to be a cold front to analyze. As long as it hasn't been pushed all the way off the map area, the chart area. And so I'm also thinking at this time, well, behind that cold front, there's probably some high pressure that's starting to push into the area. And so I'm already kind of getting a grasp as I'm doing this, what my current conditions are looking like. So the next thing that I'm going to do is we're going to do those isobars, the lines of equal pressure. Now, this is going to be really where we start trying to pop out where are those areas of high and low pressure. Now, this is not some extreme map or anything like that. It won't be quite as obvious, but we will definitely see some higher pressure and lower pressure areas. And so our highest pressure areas that I'm seeing right now are kind of in these 20s. And with isobars on the surface, we draw the lines every 4 millibars. So we do 1020, 1016, 1012, 1008, so on and so forth. So usually I'm looking for either the highest or the lowest pressure areas to start with. And I'm going to start with the highest pressures in this case, because I do see up near the top of the chart here, I'm seeing a lot of, well, not a lot, but I'm seeing a few 20s on here. And so, whoops, I got to change my color. We typically draw our isobars in black. And I see a 19 and a 2003 here. So I'm going to go right in between these two. And I'm going to come on down. And it looks like I'm going to cut there between Hayes and Great Bend. And I'm going to start curving it up. And again, you know, we're noticing that there's some pressures right here that are missing. So I'm kind of at a loss for exactly where to go. But I know that, okay, I've got 18.5 there, 18.4, 19.5. I'm probably going to go right about like that. And some of my guidance on this is because of the way the wind direction is going. Wind direction around high pressure areas goes clockwise, and around low pressure areas goes counterclockwise. So looking at our winds, we can kind of, that provides us some additional evidence of what, you know, how to draw the lines with some relative accuracy. So there's our 20 line. I'm going to look now to see if I've got any other 20s to draw, and I don't believe that I do, unless I see something pop out that I didn't see before. So the next line that we would be drawing is our 16s. So at this point, we're trying to separate everything that's above 1016 from everything below. And so I'm going to come down from the edge sort of like this and come between that 18.8 and the 15.3. And then I can curl it around back up between 14.9, 16.3. And then I'm going to go between 15.4 or 17.6. And then sort of up like that. And then we have some other lower pressures down here. Can't really see it, but that's 15.6 and 15.4. So I'm going to draw that line. We also have some lower pressures off to the east here. And so I'm going to come up roughly like this through that 16 even, 15.1, 15.6, and kind of curl that up. And that, I think, is about what I want to do on this. So now I've got my lines of equal temperature, my lines of equal dew point, and my lines of equal pressure drawn. Any questions at this point in terms of, yes? I'm sorry? Okay. The question was, what exactly is low pressure? Well, low pressure is an area that the air is moving away from. And so as the air moves away from an area, there's not as much air there. And so the pressure, the amount of forcing on that surface where the air is moving away from is not as heavy. And that's why why we're able to measure what the pressure is with a mercury barometer, because the mercury gets pushed down more in areas where the air is kind of piling up, and it gets pushed down less in areas where the air is moving away from. Now, you're not losing so much air at a location that you're gasping for breath. Now, you do feel that, though, and we talked about this a little bit last week when we moved from, say, Wichita, Kansas, to Denver, Colorado, where you're going up by another 4,000 plus ish feet in altitude, because when you go when you're heading up into the atmosphere, which is what you're doing as you're driving from Kansas into Colorado, the air is getting thinner because you're getting above more of the atmosphere. The atmosphere is kind of at one point above us. It does vary a little bit across the Earth, but the atmosphere is about 10 to 12 miles deep. And as you go up, there's less air pushing down. And so with that low pressure at the surface, and all of these pressures are standardized again to surface level pressure. So there's kind of a conversion that happens so that we're comparing apples to apples. It's basically the low pressure is where the air moves away from. And so the air kind of is lighter, and it's moving toward those areas of high pressure where that air is sort of piling up in an area. Does that kind of help? Okay. Any other questions? Oh, I think I saw that one just a fraction quicker. Yeah. Most of these, a lot of the, it's a combination of different types of stations. Most of these are manned National Weather Service stations, or just kind of sets of equipment that have been set up in certain locations. There's actually many more stations out there than are necessarily being plotted on this map. ICT here is Wichita, of course, and that would be the station of equipment that is down there at the airport. That's the official National Weather Service reporting station. But a lot of these are unmanned stations that are out there, but they're stations primarily that have been set up directly by the National Weather Service for collecting data. Over here. It is not the same in both North and South Hemisphere. It's actually reversed in the Southern Hemisphere. The spinning is caused by the rotation of the Earth. It's the Coriolis effect, which I won't get into right now. But basically, the way that the Earth, as the Earth rotates, the Earth itself kind of spins the systems as they go around the planet. So, yeah, if you're in the Northern Hemisphere, your lows spin counterclockwise and your highs spin clockwise. But if you go to the Southern Hemisphere, it's exactly reversed. Your highs are counterclockwise and your lows are clockwise. Yes. Yes. Mm-hmm. Yeah. Oh, absolutely, it does change. Yeah, the reporting stations. Some of them you can base these days. Some of them you can get almost instantaneous readouts, but officially, the Weather Service reports the changes in the temperatures and everything on an hourly basis. So usually, you'll see each hour's numbers being reported at, like, for example, we're this hour's observations were probably reported at somewhere around 104 or something like that. You'll see a slightly odd number after the hour, because it's a few minutes lag time in terms of getting that data in, and then there's going to be an additional lag time in terms of this chart itself being produced. I think back in the day, it was about 15 minutes or so before you actually see all the plots come in on the map and that sort of thing. So yeah, there's definitely some lag at all levels in terms of meteorology. I mean, what we're getting is old, is slightly old data. Yes. Mhm. Oh yeah, yeah. The question was about there's a lot of different from everything from the weather service to commercial weather firms to your TV weather stations, radio, all of that that are out there putting out forecasts. And do we look at one another's forecasts? Basically, I think is what the question was getting around to. Absolutely, I would always, that was always part of what I would go through, really almost more as a sanity check rather than, oh hey, what's this guy doing, what'd she do with her forecast. um, that was usually one of the last things that you'd look at typically. um, uh, the other big guidance, even maybe more than what you're mentioning in terms of looking at different meteorologists' forecasts, is when we would change shifts from the day shift to the night shift to the mid shift. There was always kind of a discussion handoff where the previous meteorologist says, okay, here's what I did, here's why I did it, et cetera, et cetera. And then you would kind of take over that forecast from them. And that was sort of also your starting point, along with your map analysis and everything like that. That's kind of where you started from, so that one person didn't say that the high was going to be 67 degrees and then the next person says it's going to be 45. You wouldn't radically alter and most service stations, and I don't recall what our hard and fast kind of number was at weather data. But there was certainly, there was kind of a courtesy that you wouldn't adjust forecasts in like the first 72 hours by more than a few degrees, and then it would increase as you got into the later periods, because it was always about, let's get the far out period within about 10 degrees and just slowly increase our confidence and make the little adjustments up or down in terms of temperature or in terms of precipitation, things like that as needed. But so that hopefully by the time it gets to that last 72 hours, we really don't have to do a whole lot of changes to the forecast. Sometimes you do have to still do pretty radical changes to the forecast right at the end. But for the most part, we were oftentimes making sure that the near term is already locked in, that we have the pattern recognized. You'll hear in weather service offices talking about pattern recognition, things like that. That's hot topic in meteorology and in weather forecasting, is just looking at similar patterns as they happen. And if you've seen the same thing happen many times over, it's a good chance that it's going to happen very similar again. So, and that's a real critical piece to meteorology as well, is just understanding, and that's something that's just born of experience as a meteorologist, and just building up that repertoire of, hey, this looks like what I saw 5 years ago as a setup. I remember that multiple times in my time at Weather Data, Mike Smith coming in and saying, especially on a severe weather day where he was frequently on the floor helping out, because those are the days that we were always the busiest on the operations floor, and kind of providing guidance based upon oftentimes things that he had seen before earlier in his career in terms of severe weather setup or things like that. So there's a lot of different pieces that wind up coming into and kind of going through the meteorologist's head as they're putting things together. Yes. Hmm? They don't typically have an overnight shift. In TV, your shifts are pretty similar to what they are for your news anchors. Your morning shift is coming in usually about 3:34 in the morning, and then working a few hours and then getting ready for the. What's that? It depends. A lot of them do. Some of your stations, not so much here in the Central Plains and things like that, but more benign weather regions. Your meteorologist isn't really sometimes a meteorologist. This part of the country, yeah, I mean, it would just be weird for somebody not to actually be a meteorologist presenting the weather on TV. And so, yeah, they would do their own weather analysis as well. And again, they'd look at all the other sources as well. And it's not also uncommon, especially when you're in a severe weather event, to I mean, we would occasionally place calls down to Norman, Oklahoma's Storm Prediction Center, occasionally trying to get some clarification on some of their forecasting and their thought process. A lot of that's disseminated through their discussions that they put out. That's kind of another piece of the guidance, the overall that all of us meteorologists kind of feed off of and sort of trade back and forth and discuss and things like that. So it's a lot of data to process really over a short period of time. Yes. Oh, heck yeah. Yeah, it happens all the time in meteorology. Yeah. Yeah, there's debates, discussions about what's really going on or not going on. And yeah, I mean, one of the things that is very true about the industry, whether from a commercial side or a news side or even National Weather Service side, there's a lot of competitiveness in the field. You got to have a little bit of ego behind you, when pushing your beliefs on what the forecast should be, and sometimes that works out, and sometimes you eat crow. So yeah, there's definitely a lot of back and forth on, especially when it comes to altering, a certain person who came in before you's forecast. Absolutely. Anything else before I finish this out? And then I think we're right about where we need to be for a break. Okay. I'm going to go ahead and do our final parts of this, which is basically putting our highs and our lows and our boundaries onto the map. And then once I've done that, then it's really going to start looking, aside of my really messy drawing here, it's going to start looking a lot like a weather map like you might see on TV. All right, so first I'm going to put my area of, come on, there we go. Yeah, I'm just go with the dark blue. Highs are drawn in blue, lows are drawn in red. Why that? I don't know. That's just how it's always been. So my highest numbers here with the numbers in gold are up in this area. And so I know at this point that I've got some high pressure right there because that's where the numbers are the highest. I'm also seeing kind of some lower pressures in this area and some lower pressures sort of in this area. I don't see enough to really call out a low. There's probably a weak one maybe right in this area, but I'm not going to actually analyze it. Yeah, maybe right in here. Um, I will analyze. Whoop, I got to change my pen color again. I see 3 stations right in here in an area of lower pressure where I've got winds kind of going counterclockwise, if you notice, because winds going like this, then winds kind of going like this, and then winds kind of going like that. So I know based upon at least the winds there that I've got probably it's not a real strong low, but there's definitely a low pressure area in there. All right, let me get my pen back up. So I am going to put a low on here, and then now I've got to look at where my boundaries are. And the boundaries basically are dividing lines between different air masses. So it's kind of dividing out your high pressures from your low pressures and things like that. But it doesn't always have to be just high pressure, low pressure. There's toward the end of the class, we'll look at something called a dry line, which you've probably heard of before, which is not so much a dividing line of pressure as much as it's a dividing line of moisture. So, and we care about that when we're talking about severe weather oftentimes during the summer months. So what I'm seeing here, there are some shifting winds. And so I know actually on the map it's drawn differently than I'm doing here. But I don't feel like drawing it out as a stationary front. Plus, you could argue that this is more of a trough of low pressure than a stationary front anyway, in my opinion. So that's what those dashed lines are. It's kind of marking an area, a general area, oftentimes vertically or kind of across the chart from a low pressure area where your pressures are kind of generally lower in nature. And then sometimes you'll hear a high pressure ridge. And I wouldn't normally analyze this, but just kind of for interest's sake, a high pressure ridge would be analyzed on a chart. If you ever see this kind of jagged blue line, that's calling out a ridge of high pressure or higher pressure. So I'm going to take that off though. And then I know based upon these winds from the north and the fact that I've got some moisture that is coming up, but it's being pushed sort of south with drier conditions behind it, that there's definitely a cold front here. I am noticing on the edge of the map here some shifting winds. And oftentimes, another good way to find your actual frontal line is looking for where the winds shift, but then the actual line winds up oftentimes being pretty low wind speeds, and then they'll pick up behind the front, and so I would put something right about that as the cold front. So let's think. Let's take that mental picture into our minds. And actually, before I make a quick shift here, are there any final questions on this? There'll be a little bit of time to ask questions after the break as well, and during the break if you want. Do we have any questions from online? Okay. All right. So mental picture, and now let's look at how the computer did. Like I said, the computer, and this is just kind of generated by a computer rather than a human. It is putting this in as a stationary front. Really, that oftentimes stationary fronts and trough lines can be interchanged a little bit, and frequently are. They didn't put the low on here like I did, but that's fine. And then you do see that the cold front there picked up, and definitely they're up here, there's no H drawn, but it's definitely higher pressure. If I was to look at the bigger map, the high on it, if I was looking at the national map, I think is probably more like up here. But in general, we did okay. Now, one thing we didn't do was any precipitation hashed out because this map was pretty benign and there was no precipitation to actually look at and draw out. But if there was, that would have been the next thing that we did. And in fact, we might have even done the precipitation before trying to draw the boundaries, because sometimes that finding where your precipitation is also helps you identify more exactly where that frontal boundary is, because a lot of times the storms, especially with cold fronts, are popping right along your frontal boundary. So that is analyzing a weather map in 30 minutes or so. Like I said, I would do that for the surface, and I would do it across the entire country, not just a little region of it. And then I would do it for, well, during the summer, I typically would do the 850 millibar, the 700 millibar, the 500 millibar, and the either 200 or 250 millibar level. And those upper atmosphere charts kind of also help verify that surface level. I unfortunately don't have a whole lot of time to go into that for the purposes of this class, but whatever happens on the surface is basically reversed aloft. So if I've got a surface low pressure, somewhere near that surface low pressure aloft is going to be a high pressure area up above, because not only does the wind just kind of move away from a low pressure system, there's also lifting and falling air that happen. That's part of how we wind up getting our clouds, getting our storms, and everything like that. So without further ado, I know I'm a little bit late cutting to a break. We're going to go ahead, and it looks like it is 1:56. Let's try to be back here pretty promptly at about 2:06. If any of you have some questions during the break time, feel free to come on up here, let me know. Otherwise, we'll come back at 2:06 and go into severe storms. Thanks. So I am a few minutes behind where I would normally be. So if everybody can kind of grab a seat, I do think I'll be able to get us still some time at the end if people have questions. Is there a question there in the back that I'm seeing? I'm sorry? Oh, MB is millibars. Mm-hmm. Are we a go? Okay. All right. Let me get ahead a few slides here. All right. So now in the second half of the class, we're going to kind of talk about severe weather, spotting, and we're going to look at a cross section of your stereotypical severe thunderstorm. Is what we're going to do. And like most everything else, this could be a several class session on its own. We're just going to kind of try to catch the high points as best we can. Feel free to pop in with some questions, and I'll try not to get myself too far behind in the second half of the class. A lot of people like talking about storms, which includes me, but we're going to kind of touch base on some of these topics, and then we'll close here right about 3 o'clock. So first off, I want to. We had a question last week about, with all the people who are out there chasing these days, are there ever any kind of problems with chasing and things like that? And as somebody who hasn't chased since he was in college, I can't speak to this firsthand, but I have definitely heard it from other meteorologists that it's gotten really, it does get crowded out there. A lot of people, especially now that we have, you can look at your radar. If you've got that Zoom weather app on your phone, it's got you blipped out as to your location on this map, that shows all the radar relative to your position. Back when I was in college, we did not have that. We could get one image every now and then downloaded via a very expensive cell phone connection. But for the most part, our information in the field in terms of where we were going to go, how we were going to chase the storms, that was all coming from calling back to the university and talking to some people on the phone who were looking at the weather maps and looking at the radars that we couldn't see in order to try to direct us to our location that we needed to go to for the best possibility of viewing a tornado or severe weather in general. These days, it's so easy to view where you are relative to the storms that everybody kind of thinks they can do it. But the reality is it's still, if you don't know what you're doing, it's pretty hazardous to do so. And even people who do know what they're doing, it can be very hazardous. And we're going to see in this next video where that is the case. Need to turn off. There we go. There was a tornado that many of you probably remember in here. Like a lot of the there's a lot of history with tornadoes in the Oklahoma City area. And that is because literally Oklahoma City is basically at the very heart of Tornado Alley, which we'll show a graphic about here in a little bit. But it was a particularly awful day on May 31st of 2013 in the El Reno area, which is right around Norman, Oklahoma City, all of that. A tornado touches down around 6:03, lifts just 39 minutes later, and just leaves a utter path of destruction in its wake. It was officially designated as an EF3. Now, EF means enhanced Fujita, as opposed to before, I think right around 2003, 2005, somewhere around there. It was always F0, F1, F2, F3, F4, F5. And they changed how they estimated the scale shortly after Ted Fujita, who the Fujita scale is named for, passed away. They made some alterations to it that the enhanced Fujita is based upon the physical building damage relative to kind of more current building codes rather than doing it in terms of trying to relate it directly to wind speeds. And so you've got the University of Oklahoma mobile Doppler radar for this storm. Recorded some gusts in excess of 295 miles an hour, which was one of the highest wind gusts ever recorded by a radar. Only surpassed by the 1999 Bridge Creek Moore tornado, another tornado that's very famous from that went across a very similar path as the El Reno tornado. It is still to this date the widest ever documented tornado at 2.6 miles. Now, if you want to think about that sort of relative to our current location, 2.6 miles, well, you could place the entire Wichita State University campus in that tornado and still have it reach out. And this facility here at the Metroplex would also be in that tornado. It's a huge swath that it had damage and destruction across it at its widest point. And unfortunately, it did take the lives of a few very seasoned chasers, Tim Samaras, his son, and a third chaser that chased with them. For those of you who are watching this at home, we were debating whether to just tell you the link and have you watch it on your own while we watch it here, or if we were just going to stream it for you through. There is a chance that it could, for those of you watching at home, it could be a little bit choppy. But if it becomes a problem for you to view, I'm going to tell you what to search for after we show this video. Okay, whoops. After we show this video, I'll tell you where you can also find it if you want to view it later, if it doesn't come across real well on your computer. So this video is about 7 minutes long, and I'm going to go ahead and hopefully this pulls up without too many issues. This just kind of talks about Tim, what he did as a chaser for the science of severe weather and just that fateful day a little bit. Thought I already had that open. All right. For those of you at home, if you're searching for this, you can look for, go into Google and type in The Last Chase, Remembering Tim Samaras. It's a National Geographic video on their website. I thought I already had these pulled up. Let me see if I got, yeah, there we go. I'm going to get it over here, maybe. There we go. All right. And maybe. Sorry, guys. Hopefully we get this playing. Like as a teacher in any classroom or lecture or whatever, you know that you test everything out, and then no matter how much you test it out, it still doesn't wind up working correctly when you actually try to show it to your class. All right. There we go. All right, so this is The Last Chase, Remembering Tim Samaras, I think. Let's see here. Come on.
Here watching the great clouds, the great storms, you never know exactly what you're going to find.
Okay, hang on just a second. I'm gonna restart it now that I have the video up.
You know, I've been doing this for 20 years. I enjoy the hell out of it. I really do. Out here watching the great clouds, the great storms, you never know exactly what you're going to find.
You need to get below ground if you possibly can. You know, if it's on top of you, you can't outrun it. Don't try.
We got a very large wall cloud forming, and this thing is forming rapidly.
Gary, this thing is spinning. It's getting faster and faster and faster. Gary, back to you.
So looking at that radar thing, you're thinking, my God.
All I could see was this giant wall of cloud to the ground.
I'd never seen a tornado do what this one had done.
The tornado, which had been moving to the southeast, suddenly made a turn to the left.
All of a sudden, it was over them and it was around them.
Tim was a genius, great concept to try to get a pod that would survive a tornado. That was his passion, is to make something survive a tornado and get great data and therefore understand what the air is doing, what the pressure is doing right there near the ground where people live.
Once we understand all that, the models will be better and the warnings will be better, and I think more lives will be saved.
I was shooting with Tim, Paul, and Carl since more or less 12 years. I don't know how many times I circled around the globe with them, squeezed in cars. Sometimes I wondered how a single man could be so creative. He was not only planning, but he was doing. Tim would have never risked anything for his son. Never, ever. Paul had these qualities as a videographer, and suddenly this father and son couple, they became really a great team. And for Tim, it was just a perfect match.
You have rotating rain curtains around the wall cloud. Right?
Gary, I believe it's right in there, but it's going to be rain wrapped. It's the most dangerous tornado you can have because you can't see.
Appreciate these reports. It's a gigantic tornado, at least a mile wide.
We were seriously concerned. We were on the air well ahead of time, even before the watch was issued, saying, look, there's going to be tornadoes in central Oklahoma. Make your plans now. Do it now.
Who would have expected that a tornado to do three things at once: widen out, and turn, and accelerate?
When they came back and said it's 2.6 miles wide, I think it was a surprise to most everyone.
Tim was actually a pretty laid-back guy most of the time, very easygoing. But when we were out in the field, there was an intensity. Then there has to be.
All right, the leading storm edge there is now severe warning.
He wanted to contribute to the tornado science, and it just kept him going. He was continually trying to improve his in situ measurements.
It needs to go back down the road just a little bit.
Tornadoes move unpredictably, and you don't know exactly where they're going to go. The closer you can get to the tornado before you deploy your instrument, obviously, the better chance you have of success. And that's what he did, and he was very good at it.
He also put video cameras inside, and so you could actually see this fantastic video of the inside of a tornado. So I knew there was something special about Tim.
If you were to say, which is the safest chaser that you know, I would say Tim Samaras is the safest chaser. I saw him out there and he knew when to back off. So the fact that this happened on May 31st, where he was caught in the path, is surreal to me. You know, this is the person that I would last expect to be caught in the tornado.
One of our teammates, Matt Gritch, called us saying that he was seeing rumors flying around that Tim, Carl, and Paul had been killed. And then he actually had gotten some kind of message from Tim's son, Matt, telling him that they had been killed in the El Reno tornado.
This thing is big, and it is mean looking, it's rotating, and it looks like to me it's just a matter of time because the rotation is getting stronger and stronger, Gary.
I would see these vortices that were themselves as big as an ordinary tornado. And they were wrapping around like a merry-go-round around the common center.
And if you're watching these tornadoes right here, if one forms to your left, you're history. You can't get away from it.
When a tornado gets rain wrapped, you just see rain curtains. And usually the tornado's in that rain somewhere. But the El Reno tornado, the whole area of rain was the tornado.
You might be standing there not knowing that you're very, very close to a tornado. You might not have enough time to get away.
Once that storm forms, it becomes very obvious very quickly that it's going to be a major supercell. And that's when it ceases to be fun. Before it is fun, because you're Mother Nature, you just wrestle all over the place. But once the storm starts going up, for me, it's not fun. It's not exciting to me because I know people are going to die, because not everyone gets the message. And sometimes tornadoes do unexpected things.
I was absolutely shocked. Absolutely. And actually, I can't believe it until now. I mean, I always think it can't be true. It must be, I don't know, what a bad story. I mean, I really couldn't understand it. Life is not like before anymore. And all that fun times. I mean, it's like storm chasing for me completely changed, completely.
By the time I'm old and retired, I'm hoping to contribute enough that people can take this piece and run with it. Then others, younger people, such as the college students that are participating on this, can take off and then finish out the mission when I'm long gone.
So in answer to the question, did I know Tim Samaras personally? I did not. I do some of the other colleagues of mine at the time who were a lot more into going out into the field and chasing. They were the single ones, by the way. I was married at the time, so storm chasing, even if I was really into it, was not going to be in the cards. But some of the single meteorologists would go out chasing, and they knew Tim and his son actually quite well, and said really all the same things, that you wouldn't find somebody who's really more careful than he was, and some of the work that he did is still being analyzed and studied today from some of the tornadoes that he was able to intercept. But really, the moral of the story there is, if someone who is that well trained and knowledgeable and versed in how to be safe when intercepting severe weather and tornadoes, those who do not have meteorology degrees, do not have a deep background in severe weather, should definitely not be out chasing after storms, because even after years and years and years of study, you get an outlier like the El Reno tornado that just came out of nowhere and became something unworldly, frankly. So that's kind of why I wanted to show that, is give you a little bit of background, both in terms of some of the science that is going on out in the field, trying to study and better understand tornadoes, which we still know. We know as much as we ever have, but there's still a lot we don't know about why a tornado will form in one storm versus not forming under what seems to be the identical same conditions in another storm. So fortunately, it is not. We haven't had too many tornadoes that really have approached what the El Reno tornado was. So as I kind of alluded to, I'm sorry. Yes. Average is a matter of you're talking dozens of meters rather than talking in terms of miles. I mean, most most tornadoes are your F0s, F1s. Once you get to F3, you're talking 5% or fewer of all tornadoes. Most are actually fairly weak on the scale of tornadoes. Now, I assure you, you still don't want to be involved with a F0 tornado. Any tornado is not a good tornado to be a part of, but at least with an F0, F1, if you're in your house, in your basement, you're probably going to be okay with just some, damage to walls and things like that. Once you get F3, F4, F5, then we're talking about, significant portions of buildings being destroyed. In the case of an F5, basically everything is removed from the foundation. As they said use the silly line in Twister, the finger of God is kind of what an F5 is. But here's the interesting thing, a sidebar from your question in particular, but how does the National Weather Service determine what a storm is rated in terms of the Fujita scale? We don't know what a tornado is as it's happening on the Fujita scale. Every tornado that is identified and warned on and everything like that, a National Weather Service team is actually sent out to that area where that tornado occurred, and they go and identify the damage across that path. And based upon the damage that has been done to buildings, or in areas where there aren't buildings, to vegetation, trees, things like that, based upon the damage that is taken place, is how they rate what the strength of that tornado was. So they'll usually go along the path of that storm and look for, along that path, where is the worst damage occurring. So if, say, you've got an F5 tornado, it doesn't mean it was truly F5 everywhere, every building just flattened. It means that somewhere along that path, they found a completely destroyed building. But even it goes a little bit further than that. When they find that building, then they do a little bit more investigation to make sure that it was a building that had been built to code properly, that there wasn't something else going on that would cause that building to fall down easier than it would in like EF5 tornadic winds and that sort of thing. So, yes. Oh, derecho? Are you referring to a derecho? Yeah, okay. Derecho is is again a little off topic, but it's still in the area of severe weather, so we'll discuss it real quick before I run out of too much time. Derecho is actually it's a fairly common event across this part of the country, and even more so a little bit further north. What it is it is a line of storms is called a squall line, and a derecho is really kind of a very intense squall line. It's unlike a tornado where it's rotating winds in a very small area. Generally speaking, a derecho is usually 50 to maybe even as much as 100-mile swath of just a long thunderstorm line with very intense winds. Basically, you have very, very strong updrafts that are what goes up must come down in the atmosphere. So if you have a strong updraft, you're going to have a strong downdraft somewhere. And as that downdraft comes down behind the line of storms, it hits the ground basically and spreads out really fast. It's similar in some respects. It's similar to a downburst, where you have that, and we talked very, very briefly about that last week, a downburst where you've got sinking air that hits the ground, and as it hits the ground, it blows out very fast, but it also creates a lot of low-level turbulence. It's a similar concept, but yeah, behind that line of storms, because there's such an intense updraft, there's a really intense downdraft, and as a result, that you can get winds easily in excess of 70 to 90 miles an hour in the case of a derecho. And the thing about derechos is they tend to be, a tornado lasts oftentimes, 5 minutes, 10 minutes. Derecho can last several hours going across an area, can create a pretty wide swath of tree and roof damage, things like that. Yes. Mm-hmm. No. It's more of that's a good analogy in terms of just the sheer winds, because derecho winds can definitely approach and exceed minimal tornado threshold or the minimal hurricane thresholds. It's very common, in fact, that a derecho would have tropical storm force winds to maybe minimal hurricane strength winds. But yeah, you're not going to have, there's no central circulation with a derecho. Hmm? That is, yeah. The question comment there was about Tornado Alley, which is what we're showing here on the map. And the fact that it almost feels like there's the region right here has actually become a little bit more active, and where we're at has become a little bit less active. And that's not just, that is a very well-known fact at this point in the meteorological community. And there's not a real good explanation necessarily why. Has the Central Plains just kind of gotten a little quieter over the last decade or so? I mean, when I first moved down in the early 2000s, we would still have a fair amount, it's felt like every summer, of some severe weather events here across Kansas, Oklahoma. Now, that still does occur, but it has felt over the last and there's data that says that this is not just your own perception, it is reality, that there have been a lower number of severe weather days in this part of the country relative to some other swaths of the generally less notable parts of Tornado Alley. So, and kind of the Missouri River Valley area has become considerably more active. There's been a lot of a handful of pretty significant outbreaks in this region of the country, and there's various speculation out there as to why that is. Whether it is a sign of changing climate conditions, or if it's just a natural fluctuation. Because I mean, as you see here, this is still kind of an extension of Tornado Alley. There, and another thing that's not that most people don't think about is Indiana being part of Tornado Alley, but some of our most historic outbreaks of tornadoes have been across Indiana, which is of course nowhere near Kansas or Oklahoma. So there are a lot of areas where we can get severe weather setups, but there has definitely been a downturn in this where we're at here in Kansas of severe weather days relative to, say, in the mid to late 90s, for example, where there were some very notable storms and outbreaks across this part of the country. Anything else right now? Yeah.
Okay, so the El Reno ended up being an EF3.
Mm-hmm. I think that was an F5. It was either an F4 or F5. Funny story about that. I was still in college at the time, but I was on a field study for aviation meteorology. So I was in I went to college at Valparaiso University, which is right up around there, that area. But I was in the Kansas City area at the Aviation Weather Center that is located there. And I remember seeing the radar at the time that was going on. And that was a very significant tornado. I can't remember exactly what it got rated, but I believe I want to say it was an F4, but I'm not positive. I'd have to go back and look. Yeah. And it may have been an F5 then. Mm-hmm. Okay. So I'm going to kind of move forward on things here and talk a little bit more about our severe supercells. This kind of feeds off of what we did in the first half of the class, where we were looking at the weather map, trying to analyze what the current picture of things are so that we can kind of start forecasting beyond. Well, the most critical aspects of forecasting aren't forecasting sunny days of 95 degrees. It's forecasting for, okay, what areas do we have a chance for precipitation, and what beyond that is our chance for severe precipitation, or just human impacts. Because at the end of the day, as meteorologists, we don't really have much of a point to what we're doing besides just our own personal enjoyment if what we're doing is not helping people. And that helping people is trying to protect life and property primarily. So there are three main ingredients that we have to have. We've got to have moisture. That's why we analyze the isodrosotherms for the lines of equal dew point. Higher that dew point is, the more moisture there is in the area. So that's why that's really important. When we're doing forecasting for severe weather, we usually start looking at and above. Now, on the map that we looked at, we really didn't have any of these areas. It was a benign map. But in a more severe weather kind of setup, a lot of times we're looking in particular, where is that 65 Fahrenheit isodrosotherm is, and then the 70-degree isodrosotherm, because those are the areas where we know we've got a lot of moisture and plenty of moisture for severe weather development. We're also looking for this boundary line forcing. In particular, you'll occasionally hear the meteorologists talk about a triple point. We'll look at what the triple point location is here in just a moment. And then we also, and this is again playing into, we looked at the surface, but there's a lot more going on beyond what is happening at the surface in terms of the conditions. And all of that stuff going on aloft is equally important to what's going on at the surface for us trying to determine what the potential is for severe weather. And so what we're looking at above a certain location is shearing winds, wind shear. You're looking for the change in wind direction at a point as you go up into the atmosphere. So there may be winds coming from the south across an area, but if you go up to, say, the 700 millibar level, they might be coming out of the west or the east. That shearing is what we're looking for, because if we've got shear, then we know that the atmosphere itself has some circulation going on. Excuse me. And ultimately, what we get when we're looking at the development of storm, you have horizontal circulation that develops, and then when you get that boundary layer forcing, that horizontal circulation starts turning upward because the boundary is forcing that air up. So you have this circulating air that's going upward, and that's why when you look at a supercell, which we're going to look at that cross section here in just a little bit, if you're looking at it just out your back door or whatever, and you're looking at a pretty intense thunderstorm, you'll notice as you look at the clouds that they're slightly rotating around aloft. And that's at just rotating of that entire system that's going on. And that's usually indicative of a pretty strong to severe thunderstorm. So here's that triple point that I was talking about. The area where you're going to, under the right conditions, typically find your most severe weather. Now, this is not always the case, but it is a hot area that we like to look at as meteorologists for the potential for severe weather. And it's where all three of these points kind of meet. You've got this dry line, and the dry line is not a separation of necessarily an air mass per se, as much as it is a change in the amount of moisture across an area. So right here, this area right here is going to be very, very moist. And then right behind it, the temperature doesn't necessarily change, but it gets bone dry. And that creates the right kind of setup for the development of severe thunderstorms. And oftentimes your severe storms in a tornadic situation are going to start forming in this area under the right conditions, provided that all the forcing conditions and everything like that are correct. So I'm going to just kind of cruise through these slides fairly quick because I really want to get to that last slide about the cross-section of the severe thunderstorm. We've got watches and warnings. We all know about that in this part of the country. Difference between a watch and a warning. A watch means that conditions are favorable for the development of a tornado or a severe thunderstorm, depending on the watch. And a warning means that certain criteria have been met, that event is currently happening. Really the difference primarily between whether the National Weather Service in Norman, Oklahoma will issue a tornado watch or a severe thunderstorm watch has to do with that shearing winds as you go aloft. If you don't have that wind shear, you may get still strong to severe thunderstorms, but you're very unlikely in a scenario like that to get significant tornadic activity. So that's usually that's kind of your breakdown. And then, of course, with the severe thunderstorms, we're looking for either 1 inch in diameter or greater hail, or we're looking at winds in excess of 50 knots or 58 miles an hour. There's another thing that if you're ever watching the weather and watching the warnings and watches as they come out, is looking for this specific statement that says this is a particularly dangerous situation. It's usually like the first line of the watch or warning statement, and it's all in all caps. That is a special designation for that watch or warning. That says frankly that it's a particularly dangerous situation. It means that the meteorologists that are putting that out believe that the chance for impact on life and property is significant at that point, and to really try to keep everybody extra vigilant. It's oftentimes an indication and put out when there's a high chance for a severe weather outbreak versus just severe weather within a particular area. Like, if you're gonna, the system blows up and you've got, instead of just a few severe thunderstorms here and there, you've got a line of tornadoes rolling through an area. That would be a particularly dangerous situation. Even more significant than that is, and these are really quite rare, what's called a tornado emergency. And a tornado emergency will be issued by a weather service office in the event, and this is primarily with urban areas. You wouldn't see a tornado emergency being issued across a rural area where no one's at. A tornado emergency is almost, it's kind of not just something to make sure that the public knows, hey, this is really, really going to be bad. It's also kind of a first notification for FEMA and other agencies that, have your resources ready, because this is something that is going to have a high impact on life and property. And so these are very rarely issued, but if you've got a significant tornado, usually an F3 to F5, coming through an urban area of high population density, then you'll see a tornado emergency issued. And then, as it says here, the criteria is actually kind of different from office to office. Just in kind of nomenclature, they've all kind of written it up a little bit differently, the offices that do these, but it's all basically, if a tornado is going to have a very significant impact on life and property, it's a tornado emergency. So this is one that there's been talk for years, it may or may not ever really happen, of having this actually go away and standardizing the criteria for issuing such a tornado emergency, but issuing it as a particularly dangerous situation on a tornado warning. So that's all kind of a little back and forth between weather service offices that think that they're doing the right thing versus their neighboring office doing the right thing. So, but just kind of as a general rule, if it's a tornado emergency and it's affecting your area, do not go out and watch the tornado outside, because that's the highest level of you're in a seriously threatened area. All right, so quick quiz here. You don't have to answer out loud or anything like that. Just kind of note it in your mind. What weather kills the most people? We got lightning, we got hurricanes, we got flooding, tornadoes, high wind storms, tsunamis. So get that in your head. Okay, here's your answer. Lightning kills about 50 people a year on average, mostly on golf courses. Flooding kills about 80 people per year on average. Tornadoes around 70. High wind storms around 50. Tsunamis, that was a trick. Tsunamis aren't weather. Tsunamis are geologic. Tsunami is when there's an earthquake that happens in the ocean and creates a wind because of the movement of the earth. But it is not weather, unlike what a student or two over the years have thought of mine. But what about hurricanes? Hurricanes kill a lot of people. However, most deaths in hurricanes are actually flooding deaths. If you remember back to Hurricane Katrina, really, really terrible, terrible, terrible hurricane that affected New Orleans area. I can't remember. Well, we'll never totally know what the exact death toll was from Katrina, but it was right about 3,000 deaths. There are very few events here in the United States that have had greater fatalities. And really, but most of those deaths in Katrina, just like most of those deaths in any other hurricane, are actually flooding deaths. That's why when you're in a hurricane area, they say don't go to the basement like you would in a tornado. You go to the highest floor instead. So, and I'm not going to be able to cover this as well as I really wanted to, but there is some information and resources in your slides as it relates to becoming a storm spotter and what that entails. Remember, we have radars that can identify rotation, and we warn frequently off of that rotation that there's a tornado on the ground. But until somebody actually eyeballs that tornado on the ground, we really don't know if there ever was a tornado or if that was just a tight area of circulation, but nothing actually came to the ground. And so you've got your law enforcement, EMS, firefighters, our guys on the ground who are out keeping all of us safe, who, you know, when there's severe weather, they're oftentimes the first ones to observe those severe conditions, and they're the ones that'll let the National Weather Service know that, hey, I see at this, 2 miles away from my current location at this crossroads, their tornado is on the ground. And that's how they get what's called ground truth. There's a variety of things that you need to know in order to become a spotter with a Skywarn and, with the National Weather Service. Although if you go to the Weather Service's website, there is actually reporting that you can just do as just a general person of, hey, I've got, 2-inch, 3-inch hail at my location, and you can actually report to the National Weather Service as well. They will look at those reports and compile them as they are able to verify that information. Usually, if you just say, I've got 2-inch hail falling at my location, but nobody else is seeing it, it's probably not going to make the storm reports. But if you've got a few corroborating reports within a certain area, they'll mark that as some legit reports of severe weather observed for purposes of validating their weather warnings, things like that. So these are some sources that you can go to for talking about things to be aware of for storm spotting, things like that. Spotterguides.us. This long address is for Skywarn specific training materials. And then you've got the spottersnetwork.org are good sites to look at. And lastly, in the last few minutes that I have, here's kind of a cross section of a supercell. It's certainly not all supercells look exactly like this. This is definitely the idealized supercell. If we're looking at the storm motion, the storm is moving in this case. From kind of the southwest to the northeast is a pretty stereotypical motion for a supercell. And so if I'm standing here, the storm is kind of coming toward me. And we've all kind of probably experienced this if you're kind of looking as a storm approaches, looks dark and menacing, and then suddenly the winds gust up really fast, and usually fairly briefly. Winds get really gusty as the storm comes in. You start getting a little bit of rain. Usually, a lot of those big sporadic droplets start to fall right after that gusty wind, also called a gust front, comes through. And then that wind, as it comes into the air, or the rain as it comes into the area, gets heavier and heavier. You start seeing some of these low clouds occasionally. Those are called scud clouds. They're literally little pieces of the larger cloud that's just kind of gotten torn off and torn away in some of the turbulence and some of the downdrafts that are occurring. This is also the most dangerous area for aircraft trying to take off and land. Remember, we talked about before, fairly recently in our history, we weren't very well able to identify where microbursts were exactly happening, and microbursts were responsible before we had our modern radars for a lot of aircraft accidents that would happen, especially during takeoff and landing, as planes wouldn't know what they were flying into, and would get just high turbulence up and down, and the pilots would overcorrect, and it would lead to aircraft accidents. Nowadays we have can very easily see where those areas are occurring and can steer aircraft around it. As you get close to the mesocyclone and tornado here, you start getting into hail and oftentimes, well, sometimes it's true, sometimes it's not, as was indicated a little bit in the video we watched. Once you get real close to this tornado, sometimes it'll be rain wrapped and sometimes it won't be, especially if you get to the high plains where there isn't quite as much moisture in the atmosphere, relatively speaking. Those are usually areas where you can view the tornadoes really, really nicely from a long distance away. You get across the lower central plains, and especially as you get into the Mississippi River Valley, that area of kind of the southeast, where there's a lot more hilly conditions, things like that. The storms tend to be much more rain wrapped typically, and it's much, much harder to view where the tornado is happening. But in the area of where we have the tornado, you have this lowering area. That's called your mesocyclone, and it's typically out of that mesocyclone that you'll get a tornado that would drop if the conditions are right. In this area, generally speaking, because you have rising air, not falling air, you aren't getting as much rain. And so once that storm passes, once the tornado passes, usually it clears up very quickly. The rain goes away. It might still be overcast for a little while, but you start getting breaks in the clouds and everything like that. Most of your rain and precipitation in these storms are really kind of up front of the storm as it approaches your location rather than behind it. That's why typically if I were chasing this storm, I want to actually not be to you've got northeast, southwest. So I'm actually facing the, I'm actually trying to think. I'm facing toward the northwest right now if I'm looking into this storm. And generally that northwest orientation is going to be your best bet as you're chasing a tornado to see it. Otherwise, you're getting into the rain and the hail and things like that. So typically, most storm chasers are going to try to get to the southeast of the storm so that they have the best viewing into a storm. But then you have the whole turn, some of these storms, when they get really intense, they actually start turning right and start making a right turn and start going more easterly rather than northeasterly. I saw a question in the back, and I'm right about where I have to wrap up. So, yeah. That is some of the mindset behind that, yes. And I'm going to get to those questions in just a second. Again, here's the cell phone apps. You should have them in your notes there as well, if you want. I mean, these are the weather apps that I have on my phone. AccuWeather, Zoom. I think I also have a third one. What's that third one that I have? I don't use that one enough. That one nearly as much, but it's another kind of a little bit with Sail Drone. I use that one too. You might want to look that one up. I don't know if that one's just on iOS or if it's on Android as well. But those are the three weather apps that I have on my phone. And I'll put that back up in just a second. I see some cameras trying to take pictures. So next week, just as a recap, we're going to talk a little bit about bomb cyclones, mid-latitude cyclones that get very, very deep in low pressure. In particular, the one that sunk the Edmund Fitzgerald over in Lake Superior. Pretty famous shipwreck, especially given the fact that it has a song named after it. And then we'll answer some questions about why did the meteorologist forecast 10 inches of snow, and we only got 1 inch. And we'll talk about some differences between sleet, freezing rain, and snow, and that sort of thing. So, there was the one question that you had, or one or two. I didn't capture that. I wasn't. Yeah. Let's see. Do you use and/or recommend the use of Buff Kit 19? Is the question. I'm actually not sure. I have never used that. I'm not exactly sure what that is. But I'll look into it. Yeah, thank you. Yeah, no, I'm not aware of what that is, but I can definitely take a look at that. Any other questions? I know we're right on 3 o'clock. This is a kind of one of our more fun sessions. Not that they aren't all fun, but everybody likes severe weather and weather forecasting, things like that. So yeah. Yeah, that was one thing that we couldn't really get into as deeply as maybe I would have liked to have. It's basically because that is really one of the only spots on Earth where you have a warm body of water in the Gulf of Mexico, and you've got off to the west, you've got this very dry desert area, and so you've got two very different air masses that frequently, when the winds are from the southwest and from the southeast, collide across the center part of the U.S. There's really no other place on Earth that has such a distinct differing in these air masses. And in order to have that supercellular formation that creates your very intense supercells and tornadoes and things like that, you really need that intense boundary occurring to create dramatic upward motion, along with the fact that we have the upper atmosphere winds from the westerly direction in this part of the world. That helps to, at the upper atmosphere level, kind of create that spinning as you go from the ground level up to the upper atmosphere. And yeah, it's probably a dozen sort of different little things that kind of come together across this part of the world, just this small region relatively to the rest of the world, that just isn't replicated really anywhere else. That just is perfect here. That's why, yeah, I mean, you can get tornadoes in other parts of the world, and many other parts of the world do have tornadic storms, but very few places have as intense of storms as what we have here, just because those ingredients just don't come together as ideally as they do here across the central plains. Yes. Mm-hmm. It does go somewhere. It just gets blown around and dropped, sometimes many miles away. Oftentimes in those severe, F4s, F5s, you'll find the debris landing, several miles away in some cases, because it's taken up, blown up into the circulation, and just eventually falls somewhere else. It definitely doesn't disappear. It gets spread out over a large area, and so it does make it look like it just disappeared when it really didn't. Anything else? Yes. I'm sorry, I can't hear. Okay. Yeah, there's a lot of observation of that kind of calm before the storm, and that's let me go ahead and push back here. That's there we go. That silent area that's being described is quite likely this what's colorfully named the bear cage. This is an area where you've got all of this updraft going on, but in this small area that's right near the tornado, it can get very kind of quiet, very, calm. Now, that's not always the case. Sometimes, you've got a rain wrapped situation where you got all sorts of rain still falling all around you, but it can become quite calm, somewhat similar to the center of a hurricane, where it can be very calm in that center because all that circulation's happening around your location. So yeah, I mean, that's not an uncommon observation to go from just kind of feeling eerily quiet to then sounds of a oncoming freight train as that tornado comes across. Yeah, very common. Anything else, guys? All right. Well, I'm going to let you go. If anybody else has some questions, comments, whatever, feel free. I'll stick around for a few minutes before I head on out. So thanks a lot, and we'll see you all next week.